We're going to build upon the various concepts that we've been looking at so far, and we're going to describe the quantum interferometer that we introduced in the last class in full glory. And as I mentioned, that this one experiment, if you understand it fully, you'll understand most of quantum mechanics, you'll understand most of quantum physics, because everything is in there. So please pay attention to this. We're going to talk about quantum interferometry today. And never forget that our basic motivation in doing all of this is to develop a quantum worldview. A quantum worldview, that is, how do these small particles behave? These small particles that make up all of matter, that make up energy, and so on. Even though in our daily lives we do not see these effects or the impact of quantum behavior vividly, because the quantum effects, they're all averaged out and washed away and we see a classical picture. But if you are at the proper scale in terms of temperature, size, energy, and you are looking at these particles face to face, right, then the quantum properties reveal themselves to you. So the quantum interferometer, as we all know, we're looking at 1 degree of freedom, which is the path of a photon. That's our degree of freedom that we are focusing on at the moment. Path of a photon. इधर बातें ना करें please, मुझे disturbance होती है. Path of a photon. That's our degree of freedom. So horizontal path has been designated ket 0. Vertical path has been designated ket 1. Vertical, horizontal. That's our kind of labeling, and that's our choice. So here is our interferometer. So in order to draw this, I have to first build a skeleton. My first beam splitter, my second beam splitter, my 2 full mirrors, a photon comes in the horizontal path, single photon, just one photon. Ket 0 is my input state, and we've figured out 2 output channels in the output port. So one is the possibility that the photon is going horizontally, which is the output ket 0 channel. This is the output ket 1 channel, and we place 2 detectors at the output, D1 and D2. So what we did next is that we defined the behavior of the beam splitters, and that is something we defined. So we defined that a beam splitter does something to an input ket 0 and something to an input ket 1, and we defined it. So our definition was that a beam splitter, B1 or B2, takes an input ket 0 and converts it to a new quantum state, ket 0 plus ket 1. Alright, and it takes an input state ket 1 and converts it to a similar superposition state, with the only but big difference that there's a minus sign here. Now students were asking me, how do we know this? Well, whenever light is reflected from a surface or transmitted from a surface, the electric field might change its polarization. Alright, so if you're standing on the seashore, people who are from Karachi would know this. You're standing on the Clifton beach, sun is shining and light is reflected from the waves of the ocean, and you put in a Polaroid glasses, you can reduce the intensity of the light coming into your eyes. which means that the light that has come after reflection from the ocean surface is polarized. Its phase is different from the incoming light. So whenever reflection or transmission takes place, or whenever light sees an interface between two media, air and glass, the phase can change. So the beam splitter is designed in a particular way that it affects this transformation. It achieves this transformation. So this is given to you by the optical engineer. There are other possibilities as well, and I'll give as a homework problem if the beam splitter does something differently. So that's not the unique beams, that's not unique prescription of a single beam splitter. A beam splitter can be defined in another way as well. Similarly, a mirror can be defined in another way as well. When light strikes a mirror, for example, and is reflected, a 180-degree phase shift change takes place in the electric field of light. So all of this is given to you as a truth table. You don't need to worry about where is this coming from really. It's coming from the engineering of the material of the beam splitter. All right? So this is what the beam splitter does, and each mirror interconverts ket 0 and ket 1. That's what it does. So this is something that we've already seen in the previous lecture. Now we've noticed that, and we did a calculation to this impact, that the probability that D1 clicks is 1 and the probability that D2 clicks is 0. All right? So this looks very counterintuitive and non-commonsensical. But with this progression of the quantum state, we in fact derived these probabilities. So now you have two beam splitters. Each one of them, when looked at on its own, has a 50% probability of transmission and a 50% probability of reflection. But when you put the two of them together in unison in a complete experimental setup, then they behave in a very strange fashion. That is, you have horizontal polarized photons coming in, horizontal photons coming in along the horizontal path, and only the horizontal output channel is populated, which means you're really getting only transmission, no reflection, which is very strange. And we looked at the progression of the quantum state in this interferometer. Why is this called an interferometer? Because if you recall from your basic physics that you've learned elsewhere, what is an interference pattern? An interference pattern is a sequence of bright and dark fringes, perhaps, if you're talking about light. So the general notion of an interference fringe is that you have a screen, and on this screen, if you're talking about light, you have dark regions separated by bright regions. That's your common notion of interference fringes. So you have some areas that are bright and some areas that are dark. And you have these two regions interlaced with respect to one another. Now, we call this an interferometer exactly for the same reason. This detector always clicks. So this presents a kind of a bright detector. This represents a dark detector for this configuration. All right, so that's why this is called an interferometer. So what is the lesson that we've learned so far? First of all, we know that the possibility of D1 and D2 clicking is 0. So we never get a situation in which both the detectors click in one go. In one go, only one of the detector clicks. Got it? So there is no simultaneous click on the two detectors. What does this tell us? This tells us that the photon cannot be split. All right? So we have one lesson, one big lesson from this experiment, that the photon, which is our quantum particle, therefore I also write quantum synonymously with photon, so the quantum cannot be split. This is the first big lesson that we learn. Since there are no coincidences, coincidences in English language means two simultaneous detections, and they never take place. Since there are no coincidences, we gather that the photon cannot be split. But we've also recognized that in this region here, we've created a superposition of two states. And that superposition was labeled as ket 0 plus ket 1 over under root 2. And after reflection from these mirrors, this state just preserved itself. 0 was interconverted to 1, 1 was interconverted to 0, so it's the same state here. So we had created a superposition. Now what does a superposition mean? Does it mean, first of all, we're doing experiments with single photons, and we know that the photons cannot be split. So does this superposition mean that the photon has been split into two parts? No, it doesn't, because the photon cannot be split. So it really means that a single photon is present in both arms at the same time. Right? So this photon, even though it cannot be split, it's in this superposition state, which actually means that the photon is spread out in both parts at the same time. And we say that the photon right now is behaving like a wave, because you know what the property of a wave is? If I were to take, say, a ripple tank so this is a pool of water, and I excite waves in this tank of water. So here is my source of excitation of waves, and there is a barrier. The blue represents a barrier, and there's a small slit inside this barrier. All right. Now what happens is, once again, a wave is produced. So these are secondary waves emerging from this barrier. Now we see a barrier which has two slits. What would happen in this case is that secondary wavelets will be produced from each slit. So from one source we have created two sources. Eventually we have a screen. Here we place a screen. On this screen we will see interference fringes. Correct? So we'll see regions here of water amplitude in which you will have a crest and a trough. Right? So if you drop a pebble on a lake or pool of water, you will see these waves coming out, and those waves will then interfere here and produce interference fringes. So where is the wave? The wave is everywhere inside the tank. It's taking both of these paths at the same time. The wave, in other words, is delocalized. Delocalized means being spread out in space. So the wave is delocalized here. A wave by definition is delocalized. It's spread out in space, it's spread out in time. Delocalized means it's not confined to one location. It's in both of these paths at the same time. Similarly, in this interferometer over here, in this interferometer over here, the single photon is acting much like a wave. It's acting much like a wave, hence it is delocalized. And we can say that the impact of this photon is in both paths at the same time. And that's what is meant by superposition. So inside the interferometer, this photon is behaving like a wave. Delocalized, behaving like a wave. That's another way of saying that it's in a superposition state. It's taking both paths simultaneously without being split. It's not that half of the energy is going in one path and the other half is going in the second path. That's an incorrect corollary. The proper way of imagining this situation is that the photon is really a wave and it's spread out inside the interferometer. It's delocalized. The proper physics word for this wave is a quantum field, by the way. So we've also learned that inside the interferometer, inside this apparatus, the photon is behaving like a wave. Like a delocalized wave. And in quantum parlance, in quantum language, this is called a superposition. Now the key point is that we're not making any measurement inside this interferometer. Inside the interferometer, everything is opaque to us, which means the entire interferometer, which is the combination of these two beam splitters and these two mirrors, is inside a black box, and we're not looking into the black box. We're not making any kind of measurements inside the black box. The black box is totally opaque to us. Hence, we're not trying to be over clever or over smart and trying to find out the path of the photon. Our mathematical description is coherent and it just tells us that a superposition exists. But we are not trying to be over clever and trying to find out which path the photon is taking. Our only interaction with this interferometer is through a tiny window here through which we can send in a photon, and a window here through which a photon can come out on either of the two channels. Got it? So we're not making any measurement inside the interferometer. The superposition exists. However, once this superposition sees the final beam splitter, there is some equivalent of constructive interference taking place on the bright channel and some kind of destructive interference that takes place on the dark channel. So the photon is in a sense interfering with itself. So even though there is one photon in the system, it's interfering with itself. An object can interfere with itself. So this is another kind of key lesson that we learn from this interferometer, that the photon interferes with itself. All right. Yes, please. Because we're getting an interference pattern, we do have a dark port, which means that there is some channel on which a photon will never end up. Even though, if you just had a single beam splitter, if you just had this beam splitter and a photon would come in through in the vertical direction, there's an equal probability that this photon can go on either side. If a horizontal photon came into just this interferometer at the beam splitter, it had an equal opportunity to go either way. But that's not what is happening. So one of the output channels is muted. Yes? Is
it safe to say that dark will it's interfering with itself, but bright will make it? Is that?
No, that's not a. Here it is constructively interfering on this channel, and here it's destructively interfering. Yes, please.
It's easy to imagine a wave is being deduplicated because it's a transfer of energy. So there's some parts in the space jam energy, ज़्यादा energy comes. Like a photon is a single unit, it can't be split. So how is it behaving like a wave? Is it transferring energy or something?
Well, so I'll talk about the energy in a minute. So what's happening about energy here? Remember, we're not looking inside the interferometer. So whatever energy that goes into the interferometer through the photon is carrying some energy. All of that energy remains conserved inside the interferometer and it's spread out. but we're not trying to find out where the energy is, right? So we do not try to find out an answer to the question, where is the photon? Or which path is the photon taking? We do not attempt to answer this question at the moment. What's going to happen at the end is, after the photon has issued out of the interferometer, the detector, say it clicks, it gives a sound, it gives some audible signal, blip, and one of the detector clicks. And when it says blip, it means some energy is being transmitted. What's happening is that all of the photon's energy is now being converted into an audible signal. And that audible signal has an energy, if everything is 100% efficient, that is equal to the photon energy. So all of the energy that had kind of spread out in space, it's delocalized, is now gathering together. So if all of the photon energy is spread out and delocalized inside the interferometer, and we do not attempt to find out where the energy of the photon is, then at the end, all of that energy just gathers up. It coalesces, it bunches together and kind of impinges on the detector. So at the end, all of the energy is lost to the detector. And that is what is meant by a particle. That is what a particle means. A particle just gives a localized kind of impact. So even though the photon is behaving like a wave inside the interferometer, when we measure it, it acts like a particle. And it's just a single short blip or click that the detector gives. So all of the energy, even though it's spread out in this region, and we do not dare to find out where the energy is, at the end, all of the energy musters together, coalesces, and gives a single blip. And the photon at that point behaves like a particle. So the wave determines where is that energy found on the output. But when it is being registered on a detector, the photon behaves like a particle. So the act of measurement indicates that the photon is a particle. It reinforces our idea that the photon is a particle. So in one experiment, I would say some authors would like to call this wave-particle duality, the photon is behaving like a wave. But I think in this one experiment, if you consider measurement as well, the photon is in one experiment behaving both like a wave and a particle. Wave because it's kind of delocalized inside the interferometer, and a particle because you measure it. Yes, there's a question here.
Sir, वो जो equation है, one में it's going down, so it splits it ऐसे and then back down.
No, it's not split. This is just a quantum state.
It is this and back down.
It's not up or down. This is horizontal, vertical. It's a superposition, and the power of quantum mechanics lies in this phase. This is a phase, EI pi. So the power of quantum mechanics lies in what this sign is. It's not up or down. It's superposition, and this is how we describe it. You cannot say whether it's up or down here. It's just in this superposition state. You cannot associate a physical path with this quantum state. That's why I draw these kind of strange diagrams. They represent a superposition. That's the best I can do. This does not mean that up and down. This does not mean anything else. I cannot associate a geometric path or an orientation or a direction to the photon with this. All right? Yes, please. Right, so you can design a measurement that distinguishes between these states. It's slightly more advanced, but let us get to that. Yes, please.
So you said in the interferometer the photon is spread out. So does the size change?
Does the
size of the photon changes?
So what's the size of a wave? It's acting like a wave. Is this a legitimate question? What's the size of a wave? We don't know, right? So this is not a kind of a legitimate question. The photon does not have a size. There's a wave that is spread out over the overall length of the interferometer. So for example, if this interferometer, which by the way is called a Mach-Zehnder interferometer, if the arms of this interferometer were very big and you had a very sensitive experiment, then the size of that wave would also be very big. So when you do this kind of experiment which detected gravitational waves, which is called the LIGO experiment, that was a Michelson interferometer. In a Michelson interferometer of that kind, the arm length spanned over kilometers. So the wave associated with gravity had a size expanding over kilometers. So it's not really kind of legitimate or the right question to ask. Since it's a wave, the wave is just spread out in our region of interest. Yes, please. I'll come to you in a minute.
Sir, we know that if a single photon is entering the interferometer in a Ket0 state and it's exiting the apparatus in Ket0 state as well, would it be incorrect to imagine this as some sort of wonky teleportation?
It's not teleportation, because teleportation means that you kind of it's some kind of what teleportation?
A wonky sort of teleportation, because exiting in the same Ket0 state but in a
It's not really teleportation, because you could make this state go into Ket1 as well, and I'll show you how. So teleportation is something different, but the same kind of idea does apply. Yes, please.
My question is that,
Can you speak up, please?
that once it constructively interferes, right? How does it know to keep going in this?
Yeah, we don't know this. So the question my friend has asked, how does the photon know which path would it take? So philosophers say, does the photon have some consciousness? Because this is a very deep question. How does the photon know that it must go there? We don't know this. But we do know that if you were to perform an experiment, this is what is going to happen. And I'm going to now show you some other twists to this. Now let's move on, and we'll keep on taking questions. So let's do a twist to this experiment. The twist now is, suppose we kind of do the following. Let's redraw this Mach-Zehnder interferometer. A beam splitter, perfect mirror. So one homework problem would actually be asking you if a photon came in through this side. So if the input state were Ket1, what would be the output? In fact, you will get this to be the bright detector and this will become the dark detector. So this is going to be a homework problem. Shireen, please note. All right. So the same kind of beam splitter configuration is applicable and so on. Anyway, so now let's try to change this interferometer a little bit, and we try to play Sherlock Holmes here and try to find out and investigate which path is the photon taking. So we have this kind of classical intuition and this classical upbringing that this doesn't make sense, that the photon is taking both paths at the same time and saying it cannot be split at the same time. Therefore, so let's place a detector here. So we already have two detectors at the output port, D1 and D2. Let's also place a third detector here, D3. So now we open up the Mach-Zehnder interferometer, and no longer is it an opaque black box. We have pried open into this box and put a detector here in order to kind of investigate which path the photon is taking. Now when a photon falls onto a detector, and the detectors that we're talking are of the destructive kind, the photon just vanishes, because it has now transferred all of its energy to an electrical pulse or an auditory signal, and it goes. It is annihilated, right? So measurement is a destructive process in this example. We are doing a destructive measurement. or a demolitive measurement. Demolition. So it's a destructive measurement. Measurements can also be non-destructive or non-demolitive, but that's slightly more advanced stuff. Anyway, the photon comes in through ket 1 to the state ket 0, sorry. Single photon, just one photon. Now it comes in. Now we have 3 detectors. And what do we observe now? So we can perform this experiment in the laboratory. So let's see what we observe and then try to explain what we observe. The observation now is that detector, first of all, I'm going to tell you that this detector D3 is going to click. Right? So if this detector D3 clicks and there's a probability associated with it, which is, if you can make a guess, 1 by 2, this detector is going to click with the probability 1/2. Now when this happens, of course neither of these detectors can click because the photon has been destroyed. It has already been, its energy has already been captured by the detector D3. So there's a 50% probability in this scenario that D3 clicks. And remember, when D3 clicks, neither D1 nor D2 click. And there's a half probability that this happens. Because a superposition state has been created, this is channel ket 0, and now the probability that that superposition collapses onto this channel is 1/2. You know how to calculate probabilities. So there's a half probability that this detector clicks. And when this detector clicks, let's see what happens to kind of these detectors. Neither of them clicks. We know that. So when D3 clicks, when this scenario happens, conditional upon this scenario, neither D1 nor D2 clicks. So the probability that D1 clicks, given that D3 has clicked, is 0. Correct? And the same for the probability that D2 clicks when D3 has already clicked is 0. We would all know this is commonsensical because of point number 1. The photon cannot be split. There is only one photon inside the system, and it has also already sacrificed its energy to the detector D3. So neither D1 nor D2 click in this case. Now what happens if it's also, so this is a probability of 50%. Now it's also possible in the other half of the times when detector D3 has not clicked. So now let's move into that subspace. When D3 has not clicked, what's the probability that D1 clicks? 1 by 2, right? Overall the probability is going to be 1 by 4. So in the other half of the cases, half of the times this detector is going to click and half of the times this detector is going to click. So overall, the probability that detector D1 clicks overall is 1/2 of 1/2 is 1 by 4. Correct? And the probability that detector D2 clicks is 1/2 into 1/2, 1 by 4. So we have 3 possibilities. D3 clicks with the probability of 1/2, D1 clicks with the probability of 1 by 4, D2 clicks with the probability of 1 by 4. All 3 probabilities add up to 1. Now if D3 clicks, now the key question is that something I would like to highlight is, now since both D1 and D2 have equal probability of clicking, interference is kind of gone. Because if D1 or D2 clicks, do we know the path of the photon? Question. Okay, the easy question. If D3 has clicked, can we infer from the click of D3 the path of the photon inside the interferometer? Yes. Because now it has gone through this path. If D3 has clicked, we can confirm, validate and certify that the photon has really gone through this path, because there is no other possibility for D3 to click. So now we have kind of found out the path, right? So the path, however, does not give us any interference, because neither D1 and nor D2 click. Both of them are kind of silent. If D3 has not clicked, then either of these detectors clicks. In this case, do we know the path of the photon inside the interferometer? Yes. Then we do know, and we can confirm and validate that if either of these detectors clicks, then the photon must have taken this kind of path, this top left path. So now we have information about the path. But when we have information about the path, the kind of bright and darkness of the fringes disappears. We do not have a bright and a dark channel. Both of these detectors are equally probable to fire, which means that this behaves like a classical device as it originally is meant to behave. A beam splitter, having one photon come in, there's an equal probability of the photon going to the transmit route or through the reflect route. So once we gather information about the path, the fringes disappear. The bright versus dark notion disappears. Hence, this is a really important aspect, is that if I try to be over clever and obtain information of the path inside the interferometer, which means I try to do a measurement inside the interferometer before the output port, I would have gained information about the path. The photon can still not be split, and I can tell and verify that the photon has taken this path depending upon which of the three detectors clicks, but then I will not see any interference. I will not see a distinction between a bright and a dark port. Let me finish and I'll take questions. So obtaining, so generally they use this word, which path information. Obtaining which path information precludes interference patterns. Precludes means that if I were to obtain which path information, I cannot see information about, I cannot see an interference behavior. I cannot see any wave-like behavior. So this kind of precludes. Precludes means it's mutually exclusive with interference. So then the interferometer is not behaving like an interferometer. It's not letting interference to kind of take grip. It's not letting the quantum state to interfere with itself, because we're trying to be over clever, trying to probe into the system and find out which path the photon has taken. So which path information is mutually exclusive with interference. Then all in all, the photon is behaving inside this apparatus like a particle. It's not behaving like a wave. So depending on how we measure and how we construct our apparatus and our measurement apparatus together in one go, can we decide whether a kind of quantum object behaves like a wave or a particle, whether it's going to show interference or not. Now, which path information, quantum physicists like to call this position, right? So if you talk about which path an object is taking, let's call it position. Okay, let's call it position. And interference really is about which direction the photon takes as it comes out of the interferometer, right? Horizontal or vertical. So physicists like to call direction as momentum. Okay, they just like to call it that way. Direction is momentum, because momentum is a vector. So if you have photon going horizontal, it's a horizontal momentum. Photon going vertical is a vertical momentum. So they like to call this kind of direction in which the photon comes out as momentum, linear momentum or just momentum. And by the way, another kind of kind of concept with which you can remember this is, if you remember from your A-level physics, interference is caused by waves, and waves have a wavelength. Correct? Waves have a wavelength, and associated with a wavelength is a momentum. So whenever you have a wavelength lambda, can we associate a momentum with this object? Yes. What is that? Planck constant divided by wavelength is a momentum. So whenever you have interference, means you have waves. Whenever you have waves, a nice coherent wave has a wavelength. And a wavelength, having a nice coherent wave, is essential for any interference pattern. Remember the Young's double slit experiment? It's based upon the idea of wavelengths. So whenever you have a wavelength, there is always a momentum associated with it. This is called the de Broglie relationship. And I'm not going to discuss this in detail. This is classical modern physics, which means modern physics taught in another style. I'm not adopting that style of teaching here. I'm doing a very modern, contemporaneous kind of teaching of quantum physics through this quantum kind of beam splitters and photons paradigm. Anyway, so interference is associated with momentum, and which path information is associated with position. Let's call this, give this variable kind of a symbol x. Let's call this p. Now when I want to know x, my p gets totally uncertain. When I know what p is, which means either of the detector clicks, my x goes uncertain. So this kind of complementarity between position and momentum is often called the Heisenberg uncertainty principle. So point number 7 that this interferometer demonstrates is that there is quantum uncertainty. And that quantum uncertainty is between two complementary variables or quantities, in this case position and momentum. So you want to find x, which means you want to know the path of the photon. You get totally uncertain about the momentum, which means either of the detector can click, which means you're uncertain. You have a half-half probability, which means the possibilities for the momentum are kind of extreme. The realm of possibilities for momentum goes up, and you have a pinpointed value for the position. If you're uncertain about the position, which means either of the two paths can be taken, then you can define that only one of the momentum channels is populated. So this complementarity between x and p, position and momentum. This is called one kind of version of the Heisenberg uncertainty principle. Sometimes in books, in fact most times, the useful way of writing this is that the uncertainty in position and the uns is kind of inversely proportional to the uncertainty in momentum. You are certain about x, which means this quantity is small, then delta p must be large, which means your uncertainty in p must be large. Alright, so it's a kind of seesaw effect. You know x to a higher level of certainty, then you get uncertain about the momentum, which means the range of possibilities for uncertainty is large. And sometimes, in fact most times, you could also write this as delta x delta p is kind of greater than or equal to some constant. In this case it's h bar over 2, but it has to be greater. The product of delta x and delta p has to be greater than this value. Okay, so let me finish this argument before I take questions. So starting from a simple interferometer, putting in a detector in between, we have developed these 7 big ideas of quantum physics. Waves, particles, complementary variables, uncertainty principle, don't be over clever. You want to find out the position, you will lose information about the momentum, it becomes uncertain, and so on. The measurement is kind of determining whether you see a wave or a particle. A wave is delocalized, and so on. And a measurement is impacting what you see. A measurement really is key. You put the measurement apparatus at different positions inside this apparatus, everything changes. So it's not this kind of objective reality that physics is an objective kind of field of study in which it doesn't matter how you observe two people differently. If they observe things differently, the same outcome should happen. In fact, this adds this kind of dependence on the observer into the entire picture of physics. And it in fact makes the subject of physics really very powerful. Now, what I would like to kind of introduce here, and a very useful tool, which probably you might not find in many textbooks, at least for the time being, is this concept of an uncertainty diagram. Now, what is an uncertainty diagram? So, if I look at this interferometer and would like to draw an uncertainty diagram for this, on one axis, I plot x, position or path, correct? And on one axis, I plot momentum, which in this example refers to which detector I'm talking about, correct? Which detector am I talking about in this particular example? For the time being, let's assume that this path here in this pink color is represented by number 1, Latin numeral 1. Is it Latin or Greek? It's Roman, which is Latin. So this path, let's call this 2, okay? So there are 2 possible positions, 1 and 2. So one position is 1, one possibility is 1, the other possibility is 2. And there are 2 possible detectors, D1 and D2. So let's label them as D1 and D2. Now, when interference is taking place, we are uncertain about the path, but we are certain about the momentum, because with 100% certainty is the detector D1 clicking. So if we would like to plot this scenario on an uncertainty diagram, we are uncertain about the path, we'll just draw a blob here and a blob here. I'm sorry. We'll just draw a blob here corresponding to D1 and a blob here and a blob here. Okay, good. So we have 2 possible paths, 1 and 2. So the realm of possibilities, range of possibilities. I'm using this word, realm of possibilities. In the very first lecture, I mentioned that the realm of possibilities is one way of thinking about uncertainty. The realm of possibilities for the path comprises both of these options, 1 and 2. The uncertainty in the path is large. This is the uncertainty in the path, in other words. Delta x is large. Correct? However, in either of these possibilities of the path, we are certain about the momentum, and that momentum is d1. that D1 clicks. All right. So for either of these paths, even though the uncertainty in kind of position is large, there is hardly any uncertainty in the momentum. Delta P is really small. It can't be zero. It can never be zero, by the way, because of the uncertainty principle. Because if this delta P is zero, then kind of this equation will not hold true. But let's leave that aside for a minute. The delta P is very small because only one of the detector clicks. So when this interferometer is behaving as it is intended to be, when the photon is interfering with itself, the uncertainty in position is large and the uncertainty in momentum is tiny weeny, really, really small, because we know that it's going to fall only on the detector D1. All right, so this is an uncertainty diagram depiction of the diagram that I have drawn at the top, right? If I were to draw a diagram for the scenario at the bottom part of the blackboard, X, P, kind of position 1, position 2, D1, D2. When I am confirmed that my photon takes the path 1, in fact, then if it takes the path 1, neither of the detector clicks. So this is just kind of blank in this diagram. However, when it takes the path 2, which means detector D3 has not clicked, I'm certain about the path, but I'm totally uncertain about which of the detectors is going to click. So now I have a large uncertainty in the momentum, but I have really, really tiny uncertainty in the position. So this is an uncertainty diagram representation of the diagram that I have drawn at the bottom part of the blackboard. So now let's take a 10-minute break and then we'll reconvene. I'll start off with your questions. All right, so let's get settled. Please baith jaye. So one student asked about mirrors. Who was the student who asked about kind of, yes, please can you stand up and ask the question again? And it's a very kind of cogent question. Please listen to him.
I was asking if when you say there's no measurement in the first inside the box in the first, then is the photon imparting some momentum to the mirror when it changes direction? Can't you use that to detect which path it falls on?
Now that's a brilliant question. If in this case, there's another way of detecting which path the photon takes. One case is the naive case of placing a detector, right? This tells us which path the photon takes. Another possibility is that these are mirrors which are so light, very light mirrors. Their masses would be in probably zeptograms, 10 to the minus 18 or 10 to the minus 21 grams, or the size of an electron perhaps. If mirrors were of this size, so small, then what's going to happen is that a photon will, every photon has momentum, mass and velocity. It's going to transfer some of its momentum to either of the mirrors. So if in an experiment you observe a slight click or slight tick on one mirror, it just recoils a little bit, then you would have actually done a measurement before the interferometer has kind of progressed fully. In that case, you will detect the position of the photon, because then you would have made a measurement. So one way of making a measurement is to make these mirrors ultra light, the size of probably an electron, because you would, so whenever two objects collide, if an object has to transfer its momentum, they must be of comparable sizes, otherwise nothing happens. All right, so if you were to kind of have these ultra sensitive mirrors, then yes, these mirrors can do a measurement. But in this case, in our scenario, we do not see any kick in the mirrors because they're so large. Okay, got it? The second question a student asked was really also very pertinent and quite a beautiful question is, why is this delta p? So who asked this question about the size of this delta p? I think he hasn't come back after the, okay, aapne. Can you please repeat your question?
Sir, I asked the question that why delta p not equal to 0? That's a straight line.
All right, so technically this delta p, it might appear in an idealistic way or a pedagogical fashion. This delta p must be 0 because only one detector D1 clicks. But I gave two answers to this, but let me repeat those answers. First of all, mathematically, which is not the nice way of answering this question, is that if you want to satisfy this equation, delta p cannot be 0. The uncertainty in momentum can never be 0. Okay, but what's the conceptual answer to this? The conceptual answer to this is that your detector is a kind of classical object, which means it has some size. It's a macroscopic object. It has some size. Even an electron has some size. Even an atom has some size. So if you take the finite size of this detector, so I've redrawn the detector here, and this detector is equipped with a wire which goes to an oscilloscope, gives a bleep or a speaker, which gives a click. But this detector has a finite size. And if this detector gives an audible click, then it means that the photon must have landed anywhere on its sensitive area, which really means that the photon can have a range of momentums. It could have come straight through, hit at normal incidence. It could have hit at some angle, up, down. So there is some possibility that the momentum vectors of the incoming photons, they could be spread in that. Correct? So when there is a spread in that, this means that this is not a single point here. This is a kind of a Gaussian curve, a bell curve, right? It has some finite width. And that's why delta p is not really 0. There's some smear, it can be very small smear, but some spread of this momentum. So the delta p is not really 0. Got it? Yes, please.
If we make the measurement which is not destructive, can we not have the path and the momentum at the same time?
So partial measurements, partially obstructive.
Like in the way he said on the mirrors.
You can have in between situations. Yes. Yes, please.
How did we determine the value of h bar over 2?
So that comes from this thing. This comes from Fourier analysis, I would say, and this is a classical result. So if you have a wave, the square wave, you take its Fourier transform. That is in the momentum space. It has so if you shrink it in a position kind of manifold, it expands in the momentum. So that comes from the properties of waves described by Fourier transforms and Fourier theory. Yes, please. Right, so yes, the wave, if you write a mathematical expression for the wave, it will have these this quantum field is spread out. It will have a structure, and so one way of to look at this is in as Feynman would answer this question. Feynman would answer this question in this fashion. So when you go from here to here, a single photon goes from here to here. Then there is an infinite number of possibilities for the photon to do that. An infinite number of ways in which the photon can get there. So there's one possibility that the photon goes here, one possibility that the photon goes here, one possibility that the photon. So there's an infinite variety of ways. And associated with each way, there is some what is called an action, some kind of strength to that possibility. So what would happen is that in all of these cases, all the possibilities will destructively interfere and only one will emerge as the constructively interfered winner, and that is this path. So this is called Feynman's sum of histories approach. So this is how quantum mechanics works, really. I mean, I cannot give a better or a more soothing answer than this. In fact, a really very good book which is very easy to read, and I think you can read this at this level, is Feynman's Quantum Electrodynamics, A Strange Theory of Light. Right? Let me move on. So what I would like to do now is I would like to add some drama to this. Some drama, some more drama. Let me dramatize this a little bit more. So some drama. And this is, by the way, is not a theater, it's real physics. So how do you see an object? Yeah, speak up please. Right. So light kind of, if you see an object, the light bounces off from an object and then enters your eye, registers a signal onto the retina and so on. So if you want to see something, and if you want to answer the question whether an object exists or not, you need to see it. Now, is it possible to say that an object exists without actually seeing it? Or without being influenced by it? So is there a way of detecting the existence of an object or the presence of an object in a region of space without any photon interacting with that region of space? That's the question. Yes, please? Radiation? I do not fully understand your point. Right, but the radiation needs to kind of interact, or the object needs to scatter off that radiation or emit that radiation, yes?
You're asking how to detect an object without using light, right?
No, without using any kind of energy, any radiation.
You can just feel the object.
Right, feeling the object is kind of a very crude way of seeing that it exists. I mean, but the really kind of idealistic way, any object is kind of, in order to feel an object, you need to know where it exists. So first you need to see it, right? Where is it located? Yes, please.
Maybe you can measure its gravitational field.
But still it's a field, I mean, it's still a field. Anyway, what we could do is kind of look at this experiment here. If in this case, suppose we have set up the interferometer in this fashion, only detector D1 clicks. This is the bright port, this is the dark port. Nothing comes here. So we've set it up in this fashion and we've put in multiple photons into this interferometer and verified that only this detector clicks all the time. So the probability of this clicking is 1. The probability of this clicking is 0. We have set this up, put the entire box in lock and put screws so that no one can open it. Now suppose someone, you go to sleep, someone comes overnight and just opens up the box and places a kind of an object here in this path. Right? And then he or she just packs the box back up, and then you wake up the next morning and repeat your experiment. Now this object that is placed here is now not an detector but an object, an opaque object that absorbs photons. So let me draw this scenario here. Mirror. Absorbing object. It's a perfect absorber. It just absorbs the photon. Doesn't give a click, but now we have two detectors. If a photon comes in, single photon in the state ket 0, there are three possibilities. Everything is now in a black box again, and there is a potentiality that an object might have existed in this arm, in this region of space. This is potentiality. Potentiality means mumkin hai ye aisa ho. Now there are three possibilities of detecting a photon. What are those three possibilities? What are the three kind of probabilities that we should talk about? Probability that D1 clicks or D2 clicks or none clicks, right? So we have three probabilities. Probability that none clicks, probability that D1 clicks, probability that D2 clicks. So from this discussion, what's the probability that none of them clicks? Half. If none of the detector clicks when a single photon has been issued into the system, can we say that an object exists in one of the arms? Yes. So in either of the two arms, an object exists. So now we have knowledge, or we have inferred from this outcome that an object exists. All right. And has the photon interacted with the object in this case? Yes, because the photon has now been absorbed by the object, and therefore nothing is coming out. So in this case, we detect the presence of an object, but in a very usual fashion. It's nothing special about it, because the photon has now interacted with the object, and we're not seeing the photon. It hasn't been scattered, but the absence of an outcome tells us that an object exists. So far so good. So if D1 clicks, which happens with the probability 1 by 4, as we know, if D1 clicks, can we say that an object exists or not? We are actually unsure. We are unsure. If in a single experiment a photon has been entered into the system and D1 clicks, it clicked in the first case as well when no object exists. Now it is clicking again. So we cannot be sure whether an object exists or not. It may or may not exist. So we can't be sure in one go. So what we would need to do is we need to repeat this experiment many times with many photons, many photons. And if in all of those cases it happens that D1 always clicks, then can we be sure that an object does not exist? Because then we will have a scenario very similar to this case over here. So the probability that if an object does not exist, then the probability that D1 clicks in 2 runs is going to be 1 by 4 multiplied by 1 by 4, 1 by 16, and so on. So however, if an object does exist, okay, what's the probability that this happens? 1 by 4. If this happens, can we say that an object exists? Yes. And has that object interacted with the photon? No. Because this detector D2 is clicking, which means it is registering an incoming photon. So the photon cannot be absorbed inside the interferometer. But the clicking of this detector is a telltale signature that there is some object here. So by looking at this detector, we can detect the presence of an object in either of these arms. By the way, this object could also be in this arm. So by looking at the click of an otherwise dark detector, we can say with certainty that an object exists inside one of the 2 arms of the interferometer with certainty, and the photon has not interacted with that object. So this is what is called an interaction-free measurement. Interaction-free free measurement. So we have now detected the presence of an object without light ever interacting or radiation interacting with that object. All right. So question, there was a question, yes.
I don't quite understand the premise here. Why is D2 conclusive or D1 conclusive? Can you explain that?
Right. So if so a single photon comes in. Suppose D1 clicks. But D1 always clicks in this case when no object exists. So it can click when no object exists, or it can click when an object exists. So it's not conclusive in one go. You have to repeat the experiment multiple times to draw some conclusion. So one shot will not tell you if D1 clicks, it's inconclusive. This, however, if this clicks, which happens 25% of the times, then you can detect an object without any photon interacting with it. All right. Yes, please. फिर D2 will be inconclusive, this will be conclusive. Yes, please.
इसका path से हम किस तरह explain कर सकते हैं? Maybe it takes, because we also discuss कि वो path कौन सा किस time पे ले रहा है, तो ये उस पे भी नहीं contingent होएगा कि वो path अगर ये वाला रहा है, the path I think 2 I path 1, तो उसमें it's bound to collide. But if
So that happens with probability half, yes.
okay.
All right, so let me finish this argument. Suppose when this idea was first presented by two scientists, then they kind of put some drama into this. And the drama they put was, suppose you have a bomb. Let me draw a bomb. Unfortunately, these bombs are killing humanity at the moment. But this is their example. A bomb. Now this bomb has a small ear to it, small ear with it. Now the bomb has a property that it's triggered by a single photon. Now there are two kinds of bombs, a good bomb and a bad bomb. The good bomb is a perfectly manufactured bomb that when a single photon comes and strikes the air, it triggers the bomb and an explosion takes place. That's a good bomb. The other possibility is that this ear of the bomb has a tiny orifice in it, a tiny hole in it. Which means that a photon that comes in does not interact with the bomb and it passes straight through. And there's no explosion. And this is an example of what they call a bad bomb. These were, by the way, two Israeli scientists who wrote this paper. So now, if in this path you put in a bomb, can you detect that there is a good bomb without ever exploding it? So if there is a bomb here, so if in this path I were to put in the bomb, right, in this bomb. So, and this bomb, it can be good or it can be bad. Can you detect the presence of a good bomb without exploding it? So classically, forget about quantum physics. We live in a classical world with classical beings, innocent human beings who do not know anything about quantum physics. We live in a classical world. How can you test whether a bomb is good or bad? The only way is to put in a photon and see whether it explodes or not. And what's going to happen after the explosion, you don't really know. But that's the only kind of palatable way of detecting good versus bad bombs. However, in this particular example, if this were a good bomb, then it's possible that If this were a bad bomb, then what's going to happen is that only D1 is going to click all the time. But if D2 clicks, so bad bomb will always keep this detector dark. Always keep this detector dark. Correct? Because the photon is going to pass straight through. However, if this detector clicks, which is going to happen with 1/4, with some probability 1/4, then you would know that this bomb is good. And I will give you some homework problems about this. So let's keep on thinking more about this. All right, so there were 1 or 2 questions. Yes, please. Can you speak up, please?
Potentially, could the photon being in superposition cause the bomb to explode before either the detector clicks?
So this kind of arrangement, good versus bad bomb, presupposes that if a photon exists, no matter what quantum state it exists in, it's going to explode or not explode. If it explodes, it's a good bomb. If it doesn't explode, it's a bad bomb. So if in 25% of the cases you can infer that there is a good bomb in one of the 2 arms without ever exploding the bomb. This is not possible classically. In fact, you can have variants of this experiment in which you can increase this probability to 50%, and that is by changing the reflectivity or transmissivity ratios of these beam splitters. But this is something beyond the scope. So now what I would like to shift gears a little bit is talk a little bit about another degree of freedom. And that degree of freedom is polarization. The polarization of the photon. I hope all of you get this interaction free part. Now in order to demonstrate polarization of photon, I just brought once again my setup here. So do we need to turn on this projector? Give a projector. So one idea is a photon can have multiple degrees of freedom. So far we've looked at the path a photon takes, but we can also deal with other degrees of freedom, like the momentum of a photon. We can also deal with the polarization of a photon. We can deal with the timing of a photon. When is a photon coming out? So there are different degrees of freedom. I've already talked about polarization, and I've slightly improved my demonstration from the previous time to make it more vivid, and I hope you can see what's going on. So what I have now is a light source. All right, so I have a light source, an LED, and in front of the LED is a polarizer. The polarizer polarizes the light. And then I have another polarizer on top of it. So when the 2 polarizers have their optic axis parallel, all of the light comes out. And when I keep one polarizer fixed, so its orientation remains fixed. And when I rotate the other polarizer, the amount of light coming out must change. Okay, so let me see if this works in a better fashion. So I have 2 polarizers, and what I'm going to do is I'm going to change the orientation of my second polarizer, which is a kind of analyzer. Getting darker? Actually, यहाँ नजर नहीं आ रहा यहाँ. I think I need to turn off the lights a little bit. I'm going to make it completely dark because it's very visible in front of me, but probably the projector. Ali, do we have more sheets? I'm really sorry that the camera is not showing up all the colors here. There's a kind of a blue color on that's visible to me in the naked eye, but probably this camera doesn't show it. It's a pity. I think I would need to change my camera, because if you look visually here, there is a kind of plethora of colors in front of me. Oh, I'm sorry. I think this camera, this handy cam, if you look visually, this is a kind of a zoo of colors here. Alright, so I'll do another attempt with this, don't worry, with a different camera. Alright, so let's talk a little bit about polarization. A single photon, one photon, and we're not concerned about the path now, we're concerned about the polarization. We know that there's a horizontal polarization and a vertical polarization. Got it? Alright, for a change of taste, let's use different labels for polarization, just for a change of taste, so that you're not hung up to the 0, 1 notation. Let's call a horizontal polarization ket H and a vertical polarization ket V. Now one photon could be going in one path, in one direction, and H photon literally means that the polarization is horizontal. This is ket H. And by the way, we're talking about just one photon. One photon will also have polarization. And a vertically polarized photon could be in this state. This is what the electric field of a single photon is going to oscillate. This is the direction in which the field is going to oscillate. One photon will also have an electric field, correct? Now the question is, what about superpositions? So if I look at this polarization head on, which means I'm standing here and a photon is coming in to me, and I have some kind of magical eyes which can look at polarization and electric fields, the electric field is going to oscillate horizontally. So if I look head on, I can draw this, I can depict this polarization in this fashion, just diagrammatically. Here I could draw the polarization to be vertical. Alright? But there's nothing special about horizontal vertical. This polarization could be at 45 degrees as well. So, okay, this is horizontal polarization, the photon is coming in, this is electric field. This is vertical polarized photons, electric field in a vertical plane. This is 45 degrees polarized. Let's call it diagonal. Diagonal. This is anti-diagonal. Minus 145 or 135. I can also have other kind of things. I could have this left circularly polarized photon. I could also have this, right? Right circularly polarized photon. The tip of this vector is making a circle if I look at it head on. I could also have elliptically polarized photons. So So I can have different kinds of polarizations. So if I call this cat H, I call this cat V. For diagonal, let's give it a symbol as well, D. This D is a superposition of horizontal and vertical polarization states, correct? Okay? By the way, this does not mean, when I write a quantum state in this fashion, this does not mean that a photon is either cat H or cat V. It's in a superposition, it's in both. I could also have anti-diagonal photons, anti-diagonally polarized, H minus V. So in this case, if I look head on, this is what the tip of the electric field is going to look like. I can also have a scenario in which, say, the tip of the electric field moves around in a circle like this. Let's call it left circularly polarized photon. This will also have a superposition kind of representation of this kind. Okay? Right, so now notice this phase here, iota. This phase, iota is e raised to power I pi by 2. Correct? I equals ei pi by 2. Minus 1 equals ei pi. I could have a minus sign here as well if this were going around in the other circular. I could also have these elliptical states. If I had an elliptical state like this, in which now I'm drawing the tip of the electric field as the photon moves on, then this will also have some kind of quantum state representation. I can represent this as a ket, say ket H plus the general form that I can write is some coefficient A plus some coefficient B ket V, correct? This is the entirely general form for the polarization degree of freedom. A and B are complex numbers. We know that their modulus square, you add their modulus squares, it must be equal to 1. So this is the general state of polarization of a photon. Now I can do experiments with polarization degree of freedom, and they're really important experiments because I would like to talk about in the next class a really astounding aspect of quantum physics, that is erasure. That is, by doing something in the present, you can change what happened in the past. So what I'm going to talk about in the next class is, by doing something in the present, you might alter the course of something that might have happened in the past. It's called quantum erasure. So let's now shift our discussion to Tuesday.